I'm pleased to have you with us here today for the fall return of This Is CDR and our 48th episode. This Is CDR is an online event series presented by OpenAir to explore the range of carbon removal solutions currently being researched, developed, and deployed. And to contextualize them for policy proposals, OpenAir is seeking to advance really at every level of government in the US, as well as in national and subnational jurisdictions globally. Just some quick background on OpenAir. We're a distributed volunteer network dedicated to the advancement of carbon removal solutions that are essential to solving the climate crisis. We're a global community and we're growing quickly. We work together on shared open source missions in the areas of policy advocacy, research and development, and activist CDR market development. One of the OpenAir's co-founders, Chris Neidl, is running the chat, and he'll put a link in the chat to a form where you can sign up to join us, and tons of cool stuff that we're working on, and we would love to have you be a part of what we're doing. Before we get started today, and before any This Is CDR episode, we'd like to talk about a few things, general concepts relating to carbon removal. First of all, what is carbon removal? Carbon removal is purposeful human activity to remove CO2 from the atmosphere and to durably store it in geological, terrestrial, or ocean reservoirs or in long-lived products. This definition is from the Carbon CDR Primer, which is a little icon in the bottom right of the screen here, and a great resource for learning more about CDR. It's also essentially the same definition that's used by the IPCC. Two important things when we talk about carbon removal. Number one is to disambiguate it from quote unquote carbon capture, with which it is often conflated in the media and elsewhere. Carbon capture typically means capturing CO2 from an emission source like a natural gas power plant or a cement plant. And that may or may not be a good climate solution depending on the specifics of the situation. But what it is definitely not is carbon removal. Again, carbon removal is activity, purposeful human activity to remove CO2 from the atmosphere and to store it durably. Number two, when we talk about carbon removal, it's really critical to emphasize that it is in no way, shape, or form a substitute for reducing emissions. We have to decarbonize our global economy and reduce emissions as quickly as possible, full stop. 90% of our efforts and investment in climate, really 90% plus, need to go to emissions reductions. But there's clear scientific consensus from the most recent IPCC AR6 report and elsewhere that carbon removal will be required to stabilize our economy and to achieve our climate, to stabilize our climate and achieve our climate goals at gigaton scale by mid-century. That's billions of tons per year. And that's to offset emissions that are going to be inequitable or difficult to abate, and additionally, we're going to need carbon removal in the second half of the century to restore our climate to a safer state, because we already have trillions of tons of anthropogenic CO2 in the atmosphere. We're currently at kiloton scale. Recent estimates, 2021, there are around 50,000 tons of durable carbon removal. And we are very far from the goals that we need to achieve. And so we need to be working on carbon removal now and scaling it as quickly as possible to get to gigaton scale by mid-century. Chris is putting some resources in the chat if you want to learn more about CDR, a lot of great links there. Also, again, this is our 48th episode, so you can watch the back episodes of This Is CDR to learn about some of the policy, environmental justice, and also specific CDR methods. Going to hand it over now to my colleague, Megha Raghavan, and she's going to talk a little bit about the run of show for today and also introduce our very exciting presenter. Megha.
Hey everyone. So the run of show, we'll start with a short presentation, and then we'll have a few prepared questions from Toby, and then moderated audience Q&A. So if you have any questions, please just type them into the Q&A box in Zoom. It is separate from the chat one, so please just find the right one since it helps us manage the questions a little better. The event is also being recorded, so we'll send the video link to everyone who registered, and we'll also post it to OpenAir's website and YouTube channel. All right, so this week on This Is CDR, we're very pleased to welcome Travertine CEO Dr. Lammers to present the company's innovative electrochemical process that enhances the Earth's natural carbon cycle to precipitate carbonate materials from carbon dioxide in the air, permanently storing carbon in the solid phase, while also recycling sulfates from mild tailings and generating green hydrogen. Dr. Laura Lammers is a founder and CEO of Travertine. Prior to Travertine, Laura was an assistant professor in the Department of Environmental Science, Policy and Management at UC Berkeley, and a faculty scientist at the Lawrence Berkeley Lab, specializing in environmental geochemistry. Her group studied the natural chemical processes that regulate the cycling of critical elements in the environment, regulated by mineral-aqueous interfacial reactions. The Lammers Lab sought to develop a mechanistic understanding of carbonate and phosphate mineralization and selective element separation to inspire and and improve approaches for carbon sequestration, as well as environmental remediation and critical resource recovery. Laura was the recipient of a Department of Energy Early Career Award in 2020, an LBNL Women at the Lab Award in 2020, as well as the Mineral-Aqueous Society of America Award in 2018. And she earned her PhD from the University of California, Berkeley Department of Earth and Planetary Science at the Center for Isotope Geochemistry, and a BA in Earth Sciences, summa cum laude, from Dartmouth College. So Laura, whenever you're ready, over to you.
Awesome. Thank you so much for the introduction. I'm really delighted to be here. Can you see my slides and hear me? Okay. I'm going to assume that's a yes. Okay, great. Thank you. Awesome. So I'm really excited about what we're doing at Travertine to re-engineer chemical production for carbon dioxide removal. And I want to start this presentation by seeding the idea that carbon dioxide levels in the atmosphere over geologic timescales are regulated by relatively simple acid-base chemistry. So Earth chemistry is acid-base chemistry. Carbon dioxide is what's known as an acid gas, which means that when CO2 dissolves in water, for example, CO2 in the atmosphere dissolving to a drop of water in a cloud, the CO2 undergoes what's called a hydrolysis reaction, which the CO2 breaks a water molecule and liberates a proton. And if you remember from intro chemistry class in high school, higher concentrations of protons means more acid, lower pH. And so CO2 really at higher concentrations increases the acidity of the surface environment. Now, over geologic timescales, the Earth regulates CO2 in the atmosphere by a process that's known as the URI cycle. And this is a beautiful illustration of the URI cycle online from Vesta Research. And so essentially this process starts where carbon dioxide is released from the deep Earth through volcanic activity. So it's released at a volcano into the air. And then the CO2 undergoes that hydrolysis process I described to form carbonic acid. And then this acid reacts with rocks, and the rocks actually neutralize the acidity from the carbon dioxide, and that releases carbon dioxide reactive elements like calcium and magnesium into streams and rivers that flow out to the ocean. And then finally in the ocean, we have mineralization of that carbonate into solid calcium magnesium carbonates that are small versions of this big old hunk of calcite. But this calcium carbonate can form through abiotic processes, meaning without the help of life. And that typically happens in warm, shallow seas, like in the Caribbean, or through biologically mediated processes like biocalcification, which is what a coral does to build its skeleton. And so if we want to protect biocalcifying organisms like corals, we need to make sure that the conditions are right in the ocean for mineralization to occur. Those carbonate minerals then get deposited on the seafloor over time and then taken with the ocean's crust and subducted underneath the continents through plate tectonics. And then at that point, those carbonate minerals get hit up and squeezed, and the CO2 gets released back again. And so this is the URI cycle. Again, it's a simple acid-based cycle regulating CO2 in the air over geologic timescales, meaning hundreds of millions of years timescales. So, human existence on the planet is a drop in the bucket compared to the timescale of this URI cycle. Now, I want to get into a little bit more detail on these specific chemical weathering reactions that take place in this URI cycle. So that first reaction I described, that CO2 hydrolysis reaction where the CO2 reacts with water, is shown here. So CO2 and water liberate protons. Okay, so carbon dioxide released, making an acid solution. Chemical weathering is a process by which acid is neutralized by rock-forming minerals. And so this mineral here is a magnesium silicate mineral called forsterite, which is a very common rock-forming mineral that's typical of basic or ultramafic rocks that you'll find in ocean crust or deep earth. And these rock-forming minerals can actually show up on the surface of the earth in the terrestrial environment through plate tectonics. And so, for example, Pacific Northwest, around the Ring of Fire, we have a lot of places where there are outcrops of rocks that are really enriched in these basic rocks that are very reactive with acid. And so here, this chemical reaction shows what's called a protonation hydrolysis reaction, basically a reaction where the acid is neutralized by the mineral. So in this case, acid neutralized by the mineral forms silica, which is the solid phase. It's pretty inert. And then magnesium, which is the carbon dioxide reactive element, gets released into solution. This magnesium then can combine with the carbonate from that CO2 hydrolysis process to form carbonate minerals, which again are deposited until they're released again through plate tectonism. And a really key point here is not just understanding kind of the volumes of the reservoirs of CO2 in various places in the earth, but also understanding the fluxes. And so this natural mineralization process takes about a gigaton per year of CO2, a billion tons per year of CO2 out of the air and converts it into a carbonate mineral. And so over geologic timescales, that's kind of the average rate of CO2 uptake through this process. Now, of course, human emissions are much, much faster than this, in excess of 40 billions of tons per year. And the consequence of this incredible imbalance in CO2 fluxes is, of course, the buildup of CO2 in our atmosphere. And I'm sure you all know these excess emissions are unprecedented as far as we know in the entire history of the Earth. And so this is a relatively short record of CO2 in the atmosphere over the last 800,000 years based on gas buried in ice cores, as well as some more recent data from the Keeling Curve Mauna Loa Observatory. And what you can see is, of course, that the CO2 emissions now, the rate of buildup is almost like a vertical line. You can't even see it on this scale. And so, again, unprecedented rate of increase of CO2 in the atmosphere relative to Earth history. And, you know, we've all been personally feeling the effects of climate change, right? The last 7 years have been the hottest on record. And as Toby mentioned, the recent IPCC reports have reached this consensus that not only do we need wholesale decarbonization of our energy infrastructure, so we need to completely convert away from fossil-based energy sources to the extent that we can, but we also need to couple that with gigaton per year scale carbon dioxide removal and permanent sequestration by mid-century. Decarbonization, it turns out, is going to require a lot of resource extraction. Decarbonization of energy infrastructure means producing renewable energy technologies that rely on a number of different metals that are referred to as critical metals. And these include lithium, cobalt, nickel, platinum group elements, even phosphorus is considered a critical element, although it's not for decarbonization. But all of these critical elements are going to need to be extracted at a much faster rate than we have historically done so, because there's simply not enough of these critical elements in circulation to build all the electrolyzer, build all the batteries, build all the transmission lines, all the components of electrified energy infrastructure. So the International Energy Agency has developed sustainable development scenarios that project increase of demand of these various metals relative to the rate of their mining in 2020 by 2040. And for most of these, it's more than a factor of 6-fold increase in production by 2040 relative to 2020. And so decarbonization, as Toby mentioned, that's the number one thing we need to be focusing on right now. CDR doesn't matter if we don't decarbonize, right? We can't CDR our way out of the climate crisis. We need electrified energy infrastructure. We need storage. To do this, we need to mine. But it turns out that many of these critical elements are actually associated with rocks that have the potential to neutralize acidity and react with CO2 to sequester carbon dioxide permanently. So this plot on the right here is a figure from a nice paper by Ian Power et al. That basically ranks in terms of the capacity of a given mineral, its ability to sequester CO2 permanently as a carbonate if all of the essentially acid neutralizing capacity of that mineral were converted to CO2 mineralization. And so there are some minerals that are highly reactive like brucite, which is magnesium hydroxide, which can actually sequester more CO2 by mass than the mineral itself. Forsterite is that magnesium silicate mineral that I showed you on the chemical reaction slide that you might be trying to forget right now. But forsterite has a very high potential for CO2 uptake because that magnesium in there can be carbonated, and so forth. So the rocks on the left-hand side of this chart are more favorable to promoting acid neutralization and then subsequently CO2 sequestration. And these tend to be associated with what are called ultramafic rocks. And those are those rocks that come from the oceanic crust below. And today, Power et al. Approximated, we're producing around 420 million tons per year of waste rock or tailings that are ultramafic in composition, which if we were able to tap into the entire CO2 mineralization potential of that material would be equivalent to about 175 million tons per year of CO2 sequestration, which is not bad, but it's not quite enough, right? However, if we're producing rocks more to mine the critical elements we need for decarbonization, we will be producing more ultramafic tailings. If the IEA sustainable development scenarios are correct, then we should be producing enough of this material to sequester CO2 on order of the gigaton scale by 2040. But the question then is, how do we actually unlock the full carbon dioxide removal potential of these silicate waste rocks from mine tailings? And so in the next few slides in this presentation, I'm going to talk a little bit about acid-enhanced weathering of rocks and basically how we can stimulate chemical weathering reactions by using more concentrated, strong acids so that we can do more rapid carbon dioxide removal and mineralization. I'll talk a little bit about the technological approach that we're taking here at Travertine, and then how we actually start to build an economically viable business model for large-scale carbon dioxide removal and sequestration. So I want to start out this part of the talk by showing you some data. And this is a pretty typical image from Jacques Schott's group showing the rate of dissolution. So essentially the rate of weathering or breakdown of forsterite, that magnesium silicate mineral, is a function of pH. So as you go left on this x-axis towards 0, this is lower pH, more acid solution. So 1 molar acid is going to be over here, pH 0. And what you can see is that the rate of dissolution is log linearly related to the pH of the solution, where faster rates happen in more concentrated strong acid. Okay, so acid accelerates chemical weathering of these rock-forming minerals that neutralize acidity. Okay. A number of studies have come out of a group led by Greg Dipple and now increasingly Sasha Wilson's group that show that strong acid enhanced weathering of ultramafic waste rock and mine tailings can actually maximize the yield of carbon dioxide reactive elements. And so Sasha Wilson and co-authors, Greg Southam, did a study where they used some waste materials from this chrysotile mine that was based in the UK, excuse me, not in the UK, in Canada. And they essentially took some of this chrysotile mine tailing material and they put it in closed vessels with known quantities of acids at different concentrations. And they looked to see how much of the magnesium oxide leached out, because this is essentially how much of the CO2 potential can be released through acid reaction. And what they found is that as you increase the sulfuric acid concentration, a higher proportion of those carbon dioxide reactive elements were leached from these materials, up to almost 80%. At higher acid concentrations than this, they actually saw a drop off, and they attributed that to formation of secondary magnesium silicate minerals. And so there might be kind of a threshold, but again, this was like a closed system study. So we need to do a little bit more work on kind of open system leaching concepts to understand really the maximum, but it's certainly close to 80%. Okay, just to compare this in terms of yield of carbon dioxide reactive elements to reaction with CO2 equilibrated solutions, it turns out that strong acid solutions like sulfuric acid solutions can tap into much more of the carbonate reactive elements than can waters that are simply reacted with pure CO2. So on the left here, we show essentially the amount of CO2 removal potential tapped into by reacting rock with water that's equilibrated with CO2 at just ambient pressure. That ends up giving you a solution that's pH 4, which is a little bit acidic. And this can actually dissolve reactive minerals like brucite. It can react with exchangeable or surface-bound magnesium, calcium, but it can't really dissolve wholesale the silicate, the magnesium and calcium, those carbon dioxide reactive elements. Now, if we actually dissolve the silicate minerals in strong acid, even dilute strong acid, we can actually tap into that bulk silicate fraction, which is the majority of the CDR reactive fraction. And so there's an advantage of actually enhancing chemical weathering by the use of stronger acids to do more carbon dioxide removal. Another benefit of using acid enhanced weathering is that we can actually release critical elements that are bound to or associated with. And so what this shows is some synchrotron maps, which is the synchrotron is it's a special technique, a spectroscopic technique that's used to basically understand the chemistry and mineralogy of materials. And what these are maps of elemental concentrations of various elements in a column of ultramafic rock that was leached from the top down. So we were adding, or they were, I should say, Jess and Sasha were adding acid from the top, letting the silicate minerals react with that acid. The acid was percolating through. And what happened was the critical elements, cobalt, nickel, manganese, were taken out of the silicate rock and then reprecipitated in the neutralization zone of the material, forming an enriched oxide layer. And so this is actually a way to actually enhance yields of critical elements that are left behind in mine wastes. Now, what comes out the bottom of these leach columns are sulfate solutions. And so if we're starting with sulfuric acid, this is mostly a magnesium silicate, for example, then what we end up with out the bottom is a neutral magnesium silicate, neutral magnesium sulfate solution. To actually convert that into a carbonate and sequester CO2, we need to add back in some additional alkalinity. We need to add back in 2 moles of base for every mole of magnesium that comes out. So where does that come from? A number of schemes have been put together for chemically enhanced weathering for direct air capture and mineralization of mafic and ultramafic rocks and tailings. So this is an example kind of schematic flow sheet of one of those applications in which the authors suggested adding essentially stoichiometric quantities, so 1 for 1, mole for mole quantities of acid and base to the system. So you can imagine you're sitting in a mine, you have a pile of tailings, you're trucking in massive quantities of hydrochloric acid, you're trucking in equivalent moles of sodium hydroxide to then convert that neutralized waste stream into a carbonate mineral, okay? And so the issue here is that to sequester CO2, we need to be adding almost equivalent tonnage of both acid and base as a CO2, which is really not practical at the gigaton scale. And you end up actually with net positive carbon emissions associated with this process. So how do we actually make this carbon negative and economically viable? So the approach that we're taking at Travertine is to produce carbon negative sulfuric acid. And at a high level, the heart of our process combines just 2 subunit processes. The first is a water electrolyzer that produces equal molar quantities of acid and base. And so we take in a waste solution and we generate sulfuric acid. That sulfuric acid goes into some extractive process, like enhanced weathering of tailings, like lithium extraction. And then we take the sulfate waste back into a precipitation reactor. So this is the other important subunit process of our operation. This precipitation reactor then takes the alkalinity produced in the electrolyzer and reacts that with CO2 from the air to produce solid carbonate minerals for permanent carbon sequestration. Now, these carbonate minerals could in principle be valorized as cement fillers or even green cement products. And we'd like to work on that more in the future. But for now, it's certainly permanent carbon storage. And so overall, the chemical reaction of our process is essentially you add in renewable electricity, you add in a sulfate waste, you add in CO2 from the air and a little bit of water because it's hydrolysis, and then you produce carbonate minerals, you produce sulfuric acid, and then you produce hydrogen and oxygen, which are products of the electrolysis, the water oxidation reduction reactions that are happening in the electrolyzer. Okay, so we get equimolar quantities of all of these things. And so the beautiful thing about this then is that we don't need to be continually adding in sulfur reagents, right? We can be recycling sulfate through this process continuously to minimize waste in extractive processes, but also to supply the correct balance of acid and base to actually take advantage of the carbon dioxide neutralizing potential of rocks. So right now we're in the planning phases for developing a pilot plant. And this pilot plant has the goal of demonstrating the concept for really kind of something that could be scaled to much larger carbon dioxide removal and sequestration. And it's an ex situ mineralization process that takes as an input a mine waste product, mine tailings plus or minus some waste rock. And these tailings, we essentially sprinkle acid on top. And this is a very common mining process. It's called heap leaching. It's done all over the world right now. We don't need a lot of technology innovation to figure out heap leaching, but the leachate is, we take the acid, it's neutralized by the rock. We end up with a neutral leachate. Then we introduce to our precipitation reactor. We're taking the base from our water electrolyzer, adding that to an air contactor to remove CO2 from the air, and then precipitating out carbonate minerals that we remove through a thickener and filter press. And then we recycle the sulfate solutions back into the electrolyzer to upcycle that sulfate back to sulfuric acid. And we're working with some collaborators, really excited. Sasha Wilson, who's been working on heap leaching concepts since 2009, Jess Hamilton, who's at the Australian synchrotron, Andrew Friedrich, who's at Monash University and really interested in how we recover critical elements from those artificial oxide layers that are formed. Now, in terms of life cycle analysis for this process, it can be very net carbon negative with a very neutralizing feedstock. And this is because now we don't have to bring in massive quantities of reagents, right? We're recycling most of the sulfate through the solution. And because it's water electrolysis, we're making hydrogen, we can recover some thermodynamic energy from the hydrogen that we produce as well. And so overall, the emissions removal ratio that we've modeled thus far looks very good. Now it's just a matter of actually building a pilot plant to demonstrate that we can actually meet the targets that we have set for ourselves. Now, in terms of actually making a commercially viable carbon dioxide removal process, for us, this means co-producing products that are already used ubiquitously in large quantities. It turns out that sulfuric acid is the most used inorganic chemical in the world. There's a very recent study out of a group in the UK that did a review of sulfuric acid use and projections in the future with critical element extraction and also with increased use of fertilizers. And today we use about 250 million tons of CO2 per year. By 2040, they estimate we'll use something more like 400 million tons of CO2 per year. And just so you know the math, for every ton of sulfuric acid we produce in our electrolytic process, we can sequester about half a ton of carbon dioxide permanently into carbonate minerals. And so in terms of commercial applications today, most sulfuric acid is used in phosphorus fertilizer production. And the feedstock for phosphorus fertilizer production is a material called rock phosphate, which, like those ultramafic minerals, neutralizes acidity. So the sulfuric acid goes in, reacts with the rock phosphorus. What comes out is phosphoric acid solution and sulfate waste called phosphogypsum. This bottom picture is a picture of a phosphogypsum pile. It's a calcium sulfate plus impurities. And there are billions and billions of tons of this stuff piled up all over the world. It can't really be beneficially reused in many places because it's slightly radioactive. And so, fertilizer companies are really contending with the issue of, how do we actually how do we store this in the long term? In some places, we can't actually build new plants. Like in the United States, we can't build new fertilizer plants because of the phosphogypsum waste issue. And so in our process, we would eliminate production of phosphogypsum waste by recycling the sulfur in the process, and end up with carbonate mineral products instead, as well as hydrogen, and then the sulfuric acid for subsequent fertilizer production. Now, in terms of mining application, hydrometallurgical extraction is going to be increasing a lot for the renewable energy transition. And so products of extraction with this process could be lithium, for example, extraction of lithium claystones. And an environmental co-benefit of that, in that case, would be recycling sulfate waste. So we think that there are some really good commercially viable applications for this process. And we're kind of hopefully circumventing this issue of peak sulfur that might occur in the coming decades. Now, another really important aspect of this is that we can help mitigate some of the environmental impacts of critical element extraction, which can be a deciding factor in whether or not a mining project actually moves forward and gets permitted and built. Our process helps minimize potential soil and water pollution by recycling the sulfate, because right now, plants that use sulfuric and elemental sulfur burn the elemental sulfur to make sulfuric acid, do an extraction, and end up with a sulfate waste product, which is a very linear, very conventional way that we've used resources really historically throughout human history. Right now, we're hitting up into resource limitations, right? We understand now that the planet is finite, and we need to really be leaning into these recycling processes to minimize waste and upcycle waste products. At the same time, our process can reduce carbon emissions, which can help mining companies hit their very ambitious goals for decarbonization of their emissions, so really scope 1 through 3. And so we're hoping that in many of these applications, the net carbon balance can be substantially carbon dioxide negative. And so as far as where we are as a company, we came out of the bench scale proof of concept at UC Berkeley. Just in January, the company was incorporated, and my colleague Owen Cadwallader helped me start the company back in January. And then we established an R&D facility in Boulder, Colorado, where we're right now in the process of designing and optimizing modular electrochemical cells, and then understanding kind of the kinetics and the balance of the plant so we can size that, and building a kilogram a day demonstration continuous flow system. In 2024, we're looking towards building a much bigger pilot to demonstrate larger scale carbon dioxide removal and sequestration, with an eye towards first commercial applications in 2025 plus. And what we're really trying to do is leverage the scale of the world's largest industries to tackle CO2 removal and sequestration at the scale required to solve the climate crisis, right? Phosphorus fertilizer, for example, production can get us to the hundreds of megaton scale of carbon dioxide removal, but it's really when we get into the mine waste products and reacting those with acid and CO2 that we can get into this gigaton scale carbon dioxide removal and sequestration. Just for sense of scale, sequestering 1 gigaton of CO2 as carbonate minerals is equivalent to the volume of about 800 Empire State Buildings, which is a lot, but this is only about 10% of the global volume of cement products that are used every year. And so this is very tractable when we think of the scales of the world's largest industries. Okay, and I want to acknowledge a lot of my academic collaborators at UC Berkeley, folks from civil engineering, David Sedlak, David Jaspy at UCLA, my former advisor, Don Apollo, of course, funding for Travertine from Stripe Frontier. We got a CDR pre-purchase from them we're excited about. And then our seed funders for our company, Grantham Foundation and Clean Energy Ventures. And then our kind of head of our Travertine team here, our senior engineers and our lab manager as well. So thank you so much. And I'm excited to have some discussion now.
Thank you, Dr. Lammers. That was an excellent presentation. And I want to just compliment you on how clear you were able to make a fairly complex chemical process to someone who does not understand chemistry like myself. So thank you for that, and really appreciate it. We typically kind of kick off the prepared questions just to hear a little bit more about you. And can you talk about how you got personally interested in climate, and then in your research, when did you start thinking about carbon removal, and maybe just a little bit about the Travertine, origin story, where the company came from? Obviously, it came out of your lab, but maybe just a little bit of that narrative would be super helpful, I think, for people to hear.
Yeah, happy to tell you. So I actually grew up in Houston, Texas, which is, oil and gas capital of USA, right? And so two parents who were kind of environmentalists, like really little hippies kind of. And it was funny, I just have very vivid memories of heated conversations with neighbors about, oh, should we go through natural gas or should we go straight to, electrifying everything? And so, I've kind of had this environmental problem solving ethos kind of built in for a long time. And that's why I decided to go to Dartmouth, because they had a really good earth science department, really good environmental geochemistry in particular. And so when I really got into carbon sequestration and carbon cycle was during my PhD as a part of Don DePaula's group. He happened to be leading at that time, so it was back in 2008, started this center called the Nanoscale Center for Geologic CO2, which was one of the first kind of multi-PI research consortiums around what happens to CO2 when we inject it into the subsurface at large scale, right? We've been doing enhanced oil recovery with CO2 since the 70s, but what's the ultimate fate of CO2? And can we direct that CO2 into mineralization reactions, which we all acknowledge is more stable way to sequester CO2 over the long term. And so at that time, I got really interested and wrote my dissertation on carbonate mineralization, because that's how the CO2 ends up kind of stably sequestered timescales. And then more recently, as I started my lab at UC Berkeley, we continued this research focus on carbonate mineralization and carbon cycle. But I also got into the field of selective element extraction a little bit, and was co-starting a research consortium with one of my colleagues at the Lawrence Berkeley Lab named Mike Whitaker on lithium extraction research. And through that research consortium, I had the opportunity to interact with a number of folks from the lithium mining industry and kind of learning how they were mining lithium. And I just heard this amazing story where they're planning to truck in all this elemental sulfur into the desert, which is already full of sulfur, and then oxidize it to extract lithium from clay stones, and then end up with a whole heap of sulfate waste. And so that plus, this research theme of carbonate mineralization kind of coalesced into this idea for the process that we're working on at Travertine. And so we did bench scale tests, and and now we're trying to scale up as fast as we can.
Awesome. That's great. Thank you. Second question, This is CDR presenter and a fairly prominent CDR company CEO, Peter Reinhardt of Charm Industrial. He recently was on our friend Naeem Merchant's blog talking about a proto-protocol that Charm just published with Carbon Direct. And he had a very interesting comment. I thought he said, my product is actually MRV, because that's what I need to deliver to my buyers. Can you, and some carbon removal methods have fairly, let's call it straightforward MRV, if it's a direct air capture machine taking CO2 directly from the atmosphere, which you can meter. And then some like certain ocean-based carbon removal pathways, you kind of have to use modeling and impute what the CDR is going to be. Can you talk a little bit about how your CDR will work, or how you envision it working, and maybe where you would fall in that spectrum? Can you actually meter the carbon that you're removing, or are you going to have to rely on at least you're kind of a closed system, but are you going to be able to have to rely on certain kind of modeling to kind of like impute what your carbon removal will be? Yeah,
absolutely. This is extremely important if we want to, convince people that CDR is permanent and durable, right? And so, we're an early stage company. We haven't developed any kind of strict protocol for MRV, but we want to do this in conjunction with folks that are certifying credits. But for us, as you alluded, the MRV is a little bit more straightforward than folks that are doing things kind of in situ in the field, because, not only are we doing CO2 removal through air capture, we're also producing carbonate mineral products that we can characterize very, very precisely. And so we can meter CO2 up, but we can also directly measure the total amount of CO2 that ends up in the solid carbonate products that we produce in our process. And so we can use a bunch of different solid characterization techniques for this. We can combine X-ray diffraction, thermogravimetric analysis, lots of different options to make sure that we know exactly what the mineralogy of the products that we're making are, so we know how much CO2 is sequestered.
Would the rate of carbon content vary by mineral composition, or is it pretty consistent over a given mass?
It absolutely could, particularly so in the calcium carbonate systems. We have kind of calcium rich feedstocks. It's a little simpler because most of those materials are calcium carbonate minerals without water in them, and so per mass of material exactly how much CO2 is in them for different polymorphs of calcium carbonate. Now, in terms of magnesium carbonate, that can form a bunch of different hydration states, and it can also form phases that include some structural hydroxide, which means that for a given amount of base you add, you would actually sequester less CO2. And so we want to know precisely what phase is forming, and we want to select for specific phases that have the highest degree of CO2 uptake per amount of magnesium that's released from the rock. And
so for a given feedstock, you can sort of do geochemical sampling of the output and then get a fairly clear measurement of what the carbon removal is going to be. That's
absolutely, yeah. We're going to be sitting on a pile of carbonate products that hopefully we can do something useful with, but at least we'll be inert environmentally. But we should be able to characterize those very, very precisely.
Cool. I'm going to skip a couple of the questions just so we can get to some audience questions, but two more quick questions. So OpenAir, frequent viewers of our program will know about our CDR procurement policy work. We have a state level policy called the CDRLA, the Carbon Dioxide Removal Leadership Act, that intends to get states buying CDR as part of their climate commitments. Their efforts at the municipal and local level in Colorado, actually, starting with Boulder County. And then there's a national CDR policy in the US, and all sorts of different kinds of CDR procurement policy frameworks that are being developed around the world. Can you talk a little bit about how Travertine thinks about policy, and like what kinds of policies are most important to you? I guess they might be different in terms of your initial deployment versus scaling, but maybe just a few words about how you think about policy would be great.
Yeah, absolutely. So I just want to start by saying I'm by no means a policy expert. We don't have a policy expert on the team yet, but we're trying to engage with policy to the extent possible, given our scale. And we're really excited and encouraged by all the recent legislation that you just mentioned, kind of forthcoming legislation in the pipeline. And we're also actively partnering with other kind of early stage little CDR companies trying to, I shouldn't say little, but trying to pool resources around policy advocacy for permanent CDR solutions that would distinguish them from some other approaches that have been taken in the past. As far as specific legislation that's relevant to us, we're really excited about the IRA, which has those great clean energy tax credit provisions like 45Q and 45B. A number of provisions with indirect benefits like 45X and 48C will help incentivize bringing resource extraction back to the United States, which is great in the sense that the US has stringent environmental regulations that are going to force mining to be done in the most low impact way possible, which I think is really important. We don't want to be looking back 100 years from now and say, what did we just do to the surface by mining all the things we needed to electrify the grid, right? And so I'm really excited by those provisions. The DAC hub's really exciting, bipartisan infrastructure law. I understand that these are more focused on conventional DAC where we sequester CO2 underground, but there's a push to help kind of elevate this conversation around enhanced mineralization hub, and then also project finance. That's another big thing. It's like if the government can help make loans available for plants for earlier stage projects, then that can be really instrumental in making projects commercially viable.
You mentioned the DAC hubs, and I noticed that you and your investors as well sometimes are referring to your method as direct air capture. Do you feel like you have a case for qualifying for 45Q as currently written, or are you going to need an expansion of the sort of definition of what qualifies?
I think we will. I mean, we're in our DAC process, we will need air contactors. We can't get around that. If you want to take CO2 out of the air, we're going to need an air contactor. We're just going to end up with a carbonate product. And so I do think that we will. We need to make sure that that's the case. But yeah, I think that we will. And another aspect of that is just like the longer timeline for qualifying for that is really important for us in particular. Yeah.
That's great. And we're all for it. I think that it's great. The DAC hubs do have an expanded definition currently of what carbon removal is, beyond just direct air capture. So I think that's really fantastic because we do need a range of methods to be successful in achieving gigaton scale. Okay, finally, OpenAir, we it's clear that it's very important for carbon removal methods, projects, companies to really proactively consider and address equity and environmental justice concerns, not retroactively, but proactively and upfront. The mining industry obviously doesn't have the greatest environmental justice record. Can you talk about how you think about this issue and how you plan to work with mining companies that may not have the best, equity and environmental justice, history, and then how you would think about engaging with local communities, et cetera, that are near your projects and deployments?
Yeah, thanks for the question. This is a really important issue that we care deeply about. And we think that EJ, so equity justice issues, is not such as a box to check, right? It's going to be something that's fundamental to the projects as they're designed and developed. And we need to be doing that in conversation with local community members. I think, there are other countries that do a better job than the United States in making sure that communities benefit economically from the projects they host. And so I think that's one thing as we press towards, shortening timeframes for permitting projects is, building really codified structures that make sure that communities benefit from projects locally. But also, with technological innovation, we have the opportunity to make low impact mining a reality with more cutting edge mining techniques. And, hopefully, we can kind of shift the narrative from, not in my backyard to yes, enthusiastic adoption of projects locally, because you see clearly local benefits and minimal environmental downsides. But to make that case, we have to, develop structures that reward communities, but also engage them in conversation and bring people to the table, ask, where do you want the processing facility? Do you want it here? And give people a real substantive buy-in to projects.
That's great answer. And we one of our past This Is CDRs, we had Dr. Holly Jean Buck on, and one of her headlines was really just have to engage and listen at an early stage. And I think that's so important. Well, I could ask questions all day because this is super interesting, but I want to pass it over to Mega so we can get some of these audience questions going. So Mega, there you go.
Hey, yeah, so just wanted to start with a couple of the more technical questions, and then I think there was some of the commercial side as well. So the first one we had was, how pure is the sulfate waste that you require for the process? And do you ever have issues with electrode fouling, kind of taking it beyond that threshold?
Yeah, absolutely. So, feedstocks to see, precisely what impurities do what in our system. The advantage is we're taking in a neutralized leach stream, which means that a lot of metals and silica will have precipitated out already, and so they'll be at relatively low concentrations. And so, fouling scaling from those will be less of an issue. We certainly want to avoid organic fouling to the extent we can. So some PG resources might have higher organic contents than we would want. We would want to treat them for that. And so really we're going through at this point and understanding kind of on a case by case basis, what treatments are required to make sure that we can maintain high current densities for long periods of time in our electrolyzers. And so, yeah, we're really excited about having our kilo a day system up and running so that we can really test in larger volumes some of these real feedstocks.
Oh, okay. Yeah, makes sense. Cool. The next one we had also on the technical side was, can you just talk a little bit about how you are planning to do heap leach extraction for tailings? And they mentioned that heaps are usually built with agglomerated rock rather than tailings, and for tailings you normally do a vat extraction. So just kind of addressing how your process works.
I think maybe what they're getting at is issues of permeability, because tailings tend to be very fine-grained. I'm not sure that that's what they're getting at, but so permeability issues are definitely something that we're thinking about in designing the heap leach pad. There is a world in which we could do this in a reactor or vat, but it's a little bit simpler and cheaper to do a heap leach. We're talking about kind of incorporating particle size distributions, incorporating some coarser waste rock to help maintain permeability. But that's something that we're going to, Grantham Environmental Trust has promised close to $1 million towards the really specific design engineering of the heap leach pad for the tailings. So we're really excited about that.
Okay, great. We had a couple questions about sort of the inputs to the process. So is there enough subsurface water associated with the minerals that you need that could be used for electrolysis? And if not, what is the primary source of water?
That's a good question. So in most of the extractive processes we're looking into working in tandem with, there will be water used in the process. And so there's already water recycling through. The acid leaches are kind of dilute acid leaches. And so the net water addition will be relatively small because most of these projects are actually zero liquid discharge. So any water used in processing can't be discharged as water. And so they're happy to get rid of water through electrolysis, right? And also through water bound in minerals. And so that's one thing. But, working in the Pacific Northwest where water is more abundant, at least now, might be a good place for enhanced weathering of tailings, for example, when, there's not already a process in place processing those tailings.
Okay, got it. Yeah, and then we got, I guess, more broadly a question about just, are there any other material bottlenecks that you might face? Are there any critical minerals that you need for the process, or is that not an issue?
I mean, right now, I don't see that as an issue. I mean, there's just so many uses of sulfuric acid in various concentration ranges that there's a broad funnel of applications for our process, and we're trying to narrow it down, focusing on the most suitable feedstocks for real carbon negative applications, and then also just the least technologically challenging to start out with, right? We're going to start simple and get more complicated.
Okay, got it. We got a couple of people asking about the difference. Well, I'll do them one by one. So someone says, I'm curious about the use of sulfuric acid as it's far less effective at leaching calcium than magnesium. Why choose sulfuric?
Yeah, so that's a good point, because what happens with calcium minerals is, and this is exactly what happens in fertilizer production, is calcium sulfate is relatively insoluble. And so you form a calcium sulfate solid product. And so if you heap leach, for example, calcium silicate, you might end up actually precipitating out gypsum or calcium sulfate in the pile, meaning that what you get out is no more concentrated than equilibrium with that phase. And so, we're developing a process to work with gypsum as a feedstock. And so in principle, we could still have a gypsum feedstock feeding it. We just have to make sure that we're accounting for the sulfur balance, making sure we're able to get the calcium out as quickly as possible. So that's really, I think that's the problem they're alluding to, and can definitely make it more challenging to work with calcium silicate rocks. But, on the other hand, calcium silicate rocks are a lot more rare than magnesium silicates.
Right. Okay. Makes sense. I'm going to move over to some of the more, I guess, sort of commercial or like life cycle analysis related questions. So the first one, pretty basic. What is the energy intensity of the process per ton, per turn of sulfuric acid, or whatever units you want to think about it? And then how does that vary between calcium versus magnesium systems?
Oh gosh, the units, I don't always think of that unit, but
right,
so
yeah,
in terms of energy intensity, this is the crux, right? This is the question, because water electrolysis is energy intensive. And so we have demonstrated at the bench scale and the small scale that we can achieve acid production with an energy intensity of around 0.2 kilowatt hours per mole sulfur, which would be, oh gosh, you can do the units conversion, 0.2 kilowatt hours per mole sulfuric acid. And that's equivalent essentially to the energy intensity of chloralkali. And we've shown we can do this at current densities that are kind of industrially relevant, but probably not as high as the current densities they're using for chloralkali at this point. And so, we think this process can be very efficient. We're trying to understand questions around how durable are our process components in the various feedstocks. What are the failure modes? Just getting ahead of any issues that we'll have with the electrolyzers.
Okay, got it. That's actually maybe a good lead into the next question, which is, sounds like this process is highly dependent on cheap electrolysis. Are the current commercially available systems good enough for the techno-economics to work out, or how do you see that developing?
Yeah, so our electrolyzer is a little different than like conventional acid or alkaline electrolyzer. It's kind of a combination of the two in a way. And so we can use components that are already commercially available. We can use the cathodes from alkaline electrolysis, and from acid electrolysis. We can use membranes that are already sold for dogs. The question is, can we demonstrate that they can operate durably at large scales for large time periods? And that's why we're working up through these pilots. Very exciting.
Cool. I'm going to do one last question before I hand it back to Toby to close things off. So just thinking about scale, you mentioned some of the scale of the problem and some of the different numbers in terms of like what amounts of carbon dioxide are emitted and captured in various processes. How much of that sort of 40 gigatons per year that you said humans emit will Travertine potentially be able to address when you think about scaling up?
I mean, the guiding star, right, is the ability to achieve a gigaton per year carbon dioxide removal and sequestration. And so that's what we're thinking of as our guiding star, but that's just a staggering quantity of CO2, right? And just a massive, massive amount of infrastructure, right? And so I'm really excited to work towards that. We really need to be able to do CDR at that scale. And I hope we can scale up that big.
Great. Well, this has been great. Thank you so much. And Toby, I'm going to give it back to you to just finish us off.
Great. Thank you, Mega. And thank you, audience, for so many great questions. And especially thank you to Dr. Lammers for being with us today. And I know you've got a lot on your plate running an early stage CDR company, but it was really great to learn more about what you're doing with Travertine. And again, it was a really fantastic presentation. So thank you so much.
Thanks for having me.
Couple notes as we close just about what we have coming up with OpenAir. Number one, and we've talked about this before on this program, but we continue to work on a citizen lobbying push for the federal Carbon Dioxide Removal Leadership Act. So basically anywhere you live in the country, you can call your local representative and ask them to support this bill. There's also a Senate version, so you can call your congressional representative and then your senators. So please, there should be a link in the chat to sign up for OpenAir, and we have an entire script set up and a very easy to onboard system for you to kind of engage in the citizen advocacy. Similarly, we are working on state level policies. So if you live in New York, we have an active bill in New York. We will soon have active bills, we hope, in Colorado, the home state of Travertine, and in Massachusetts. So if you live in those states, it would be great for you to connect with us and to get involved in those efforts. And so that's one thing we have coming up. Coming up on This Is CDR, we're kind of kicking back in for the fall after taking a short summer break. We're super excited next week to have Dr. Jessica Cross from the National Oceanic and Atmosphere, NOAA, the government agency that was most likely to be working on MRV and regulations for ocean-based CDR. And she's going to teach us about a systems level perspective for MRV for ocean-based CDR. On October 4th, we have an early stage enhanced rock weathering company, basically grinding up basalt and putting it on agricultural lands, called Lithos. They recently raised some funding. They are also, like Travertine, one of Frontier's recent portfolio of purchases. On October 11th, another recent Frontier purchase, Rep Air Carbon, which is an Israeli-based electrochemical direct air capture company. And we will be announcing additional sessions in the coming weeks. So we got a lot coming on, and we'd love to see you. Next week, again, Dr. Cross, who will teach us about the thorny problem of ocean-based MRV for ocean-based CDR. Thank you again for being with us, and thank you to Dr. Lammers for such a great presentation. Everyone be well, and we will see you next week.